Okay, Chapter 4, Section 6, Optimization. So optimization problems are problems that involve finding the absolute maximum or minimum of functions. Common optimization problems involve finding area, perimeter, maximizing revenue and profit, and inventory control. Okay, example 1, area and perimeter. What are the dimensions of a rectangle with area 225, area of 225 square meters, that has the least perimeter, the smallest perimeter possible? Okay, so first of all, let's think about different possible answers. So for example, we could have one rectangle that looks like that, and then have another rectangle that looks like that, just kind of randomly picking some rectangles. So let's say that in this one we have L equals to 45, and this one W equals to 5. And over here, let's say L equals to 25, which means W equals to 9. So we know that the area equals to length times width. So in both of these rectangles, we have area that is going to be equal to 225. So notice that in here, the area equals to 45 times 5, which is equal to 225. And over here, the area is equal to 25 times 9, which is still going to be equal to 225. So we have two different rectangles that both have the same area of 225. However, if you think about perimeter, perimeter is the distance all the way around. So in this rectangle over here, the perimeter is going to be 25 plus 25 plus 9 plus 9. Right? Think about having to build a fence around this rectangle. That's how much fencing you're going to need. So that's equal to 50 plus 18. That's equal to 68. 68 meters of fencing. Right? Whereas over here, to build this rectangle, we would need to do 45, 45. We would need 45 plus another 45 plus another 5 plus another 5. Right? So 45 this way, 45 that way, 5 and 5. A total perimeter around our rectangle of 90 plus 10 equals to 100 meters. 100 meters. Versus 68 meters. So this shape over here is takes up less perimeter, right? It has a smaller perimeter, traps the same amount of area as this one. So if you were concerned with minimizing the amount of fencing that you use, maybe the fence is really expensive or it takes a lot of work to install it, maybe that's what you're concerned about, so you want to minimize it and still have the same area. On the other hand, there might be some reason for why you want it to be this shape, and so you might be okay with spending more, right? But all I'm really pointing out is that there are different dimensions that you can do and still trap 225 square meters. So what we want to do is find the dimensions that has the least perimeter, the smallest perimeter. Okay, so to do that, let's do this one more time over here. So let's do another rectangle now. So let's say I arbitrarily have a rectangle, and let's say that this is L and W, of course. So we know that the area is equal to length times width. And we are also talking about perimeter, right? So we want to minimize the perimeter. So we know that the perimeter is going to be equal to twice L plus twice W. That's the perimeter to go all the way around, the fencing required. So just to get rid of this word, we're going to use the letter A. So this is one formula. A equals L times W. And here's another formula, and we'll say P equals to twice L plus twice W. We wanted to optimize the perimeter, right? So reading the question one more time. The least perimeter. We want the minimum of the perimeter. So optimize the perimeter. So we want to work with the formula or the equation for perimeter. This guy right here. But there are too many variables right now. There's a P, there's an L, there's a W. Just simply focusing on this formula at this point would kind of lead us into a difficult situation. Okay, so what we have to do is use this other formula to reduce the number of variables that we need for this equation. Remembering that we are told that the area has to be 225, so that's not really, that's a constant, that's not a variable. So we have for us that 225 must be equal to L times W. So we can solve for either one of these letters, it doesn't matter which one. So let's say that we solve for L. So then L is equal to 225 divided by W. And then that is what we take and bring right over there and plug it right into there. And now we have that the perimeter is equal to twice 225 over W plus 2W. Okay, so now what we've accomplished is we've reduced this from having three variables. Perimeter is a variable. L and W are variables. So we had three variables here. We were able to reduce it down to an equation that only has two, the perimeter as a function of the width. So now this is sort of function notation. So we could write it this way. P of W equals to 225 times 2, which is 450. To 450 divided by W plus 2W, right? So it's a function of W. Okay, so now this is what we want to work with. Okay, so the first thing we want to think about is what is the domain of this function? This is a rational function. We know that we cannot let W equal to 0. But as long as we don't let it equal to 0, it could really be anything else. So this is a function where P of W is continuous. On all real numbers except W is not allowed to be equal to 0. However, this is in an abstract mathematical world. When we consider that this is a problem coming from a real world situation, we know that in the real world, lengths have to have positive answers, right? So we have to have an L value that's strictly greater than 0. We can't have a rectangle where one of the lengths was 0, right? Or the width. If you think of a box where the width is 0, that doesn't make sense in the real world. So for us, we also have to consider that both L and W cannot be equal to 0, and they can't be negative. So L can't be 0, W cannot be 0, because then you'd have a rectangle where one of the dimensions was 0, then you have a line, right? Okay, and also you can't have negatives. So what that means is that both L and W have to be strictly greater than 0. So that becomes our domain for this function, that we need W to be strictly greater than 0. Okay, so now that we have our function here, let me write it over here. We have P of W is equal to 450 divided by W plus 2W. Next, let's find the first derivative. So to find the first derivative, it might be useful to rewrite this function. It's equal to 450 W to the negative 1 plus 2W. And now the first derivative is then equal to negative 450 w to the minus 2 power plus 2w. And then we can simplify this a little bit. By saying that the first derivative is equal to negative 450 divided by w squared plus 2w, and then w is equal to negative 450 divided by w squared plus 2w, and we're going to multiply the numerator and denominator of this function by 2w. That'll get us to the first derivative is equal to negative 450 over w squared. Oops. Sorry. First derivative here, correction. This is a 2, not a 2w. Okay, there. So first derivative is that. Okay, so then this becomes 2w squared over w squared. And so the first derivative becomes, and I'm going to move this around, becomes 2w squared minus 450 divided by w squared. Okay, so now we got to find the partition points for this function. So the partition points are going to come when the denominator is equal to 0, right? So p prime of w equals a does not exist when the denominator equals to 0. So w squared equals to 0. I'll put when w squared equals 0. So w equals to 0 is one of the partition points. And also, another partition point will come when the first derivative is equal to 0. And in a fraction, that'll happen when the numerator is equal to 0. So that's when 2w minus 450 equals 0. We can factor out a 2. We get w squared minus 225 equals 0. So we get 2 times w plus 15, w minus 15 equals to 0. So one of the answers will come from this, which means, from that, which means that w equals to negative 15 is going to be one of our partition points, and w minus 15 equals to 0 is another partition point, or w equals to positive 15. So our function has 3 partition points. However, when we think about our restriction of our domain, we know that w has to be positive. We cannot have a rectangle where the width is 0. That wouldn't really be a rectangle. And we can't have a rectangle where the width is negative. So for this particular word problem, a real world situation, we can drop those 2, and then this is the only partition point remaining, so we upgrade it and call it a critical point. Right? A critical point is a partition point that is also in the domain of our function. So we found our critical point of interest. So the only critical point is w equals to 15. So that might be our answer, but we're not done yet. We have to confirm that that's our answer. So here's what we're thinking. We're looking for a place to minimize the perimeter value, right? The smallest perimeter value possible. So we want to identify, we want to check if this is in fact a local minimum. To check to see if it's a local minimum, we can check to make sure that the first derivative of our function is increasing at w equals to 15. So consider the following. Let's say we had just some random thing like this. Say we have a function like that. Then this point right here would be a local minimum, right? And notice that the tangent lines like this would look like that. Just in general, this is what describes a local minimum. We have concave up. Good. So notice that the slope here is going to be some big negative slope. Big negative. And then it goes to a smaller negative. Say over here we still have a small negative slope. And then at this point, it's a tangent. The tangent line is horizontal, so we know the slope equals 0. And then we have a small positive slope over here somewhere. Small positive slope. And then it builds up to a much big positive slope. Just roughly, right? And I keep saying slope, but then that's also the derivative, right? The derivative at each one of these points. So f prime. So instead of saying big negative slope and all that, we could just say that the first derivative, f prime of x, is a big negative at this level. F prime of x, the first derivative, is some small value somewhere in this area. Slope equals to 0 for that line means that f prime of x equals to 0 somewhere there. And then again, for these, the first derivative is some small positive there, and that first derivative is some big. So we're going from big negative to small negative to 0 to a small positive to a big positive. We know that that first derivative is increasing. So f prime of x is increasing. And it's going from negative slopes to positive slopes. Going from negative slopes, negative values, to positive values. Okay, now f of x is just kind of a generic term. I'm used to using it. But in our particular word problem, we're looking at the function p and the independent variable w. So we should be looking at p prime of w. So I could have just written this as p prime of w must go from a big negative there to p prime of w must go from a small negative. P prime of w equals to 0, somewhere around there. And then p prime of w is a small number here. Finally, some p prime of w is some larger value there. Okay, so the point is that p prime of w is increasing, and it's going from a negative value to a positive value. Okay, all right, so in order to confirm that we really do have a local minimum at this point, we need to check that the first derivative has a sign change at that point from negative to positive. That's what we need to do. So let's create a sign table for the first derivative. Come back over here. Right, so we're doing the following. Check if w equals to 15 is a local min. Okay, so we're going to create sign chart. Here is 15. So we're going to pick a value to the left of 15. We're going to pick a value to the right of 15. Keep in mind that we're only interested in values that are strictly greater than 0. So why not pick a nice convenient number? How about 1? 1 is in there. And another nice convenient value, let's just pick 20. It's definitely in there. Okay, so now we just want to see if the first derivative is positive or negative with those values. So f prime, the first derivative, p prime of w. So p prime of w is equal to 2w squared minus 450 all over w squared. So let's Let me just erase these guys then. This guy in there, this guy in there, this guy in there. So if we replace those w's with a 1, put a 1 there, put a 1 there, put a 1 there. 1 squared is 1 times 2 is 2. 2 minus 450, that would be negative 448. And so my whole answer is going to be negative. That's all that really matters, right? So we've established that the first derivative is going to be negative there. So p prime of w is negative there. This is the w axis. Okay, so now let's do the same thing for the number 20. So we'll have p prime of blank equals to 2 times blank squared minus 450 all over blank squared. And so now we're going to evaluate it at 20. 20 there, 20 there, 20 there. 20 squared, that's going to be 400 times 2 is 800. Minus 450 gives you a positive value, and the denominator is also positive. So I can tell that this whole thing is definitely going to be positive. So that means that all of these are positive. So just as we had suspected, the first derivative changes from having a negative value to a positive value here, and we've already established that p prime of 15 does in fact equal to 0. So we go from negative to 0 to positive. That establishes that w equals to 15 is a local minimum. So w equals to 15 is a local minimum. Okay, so we can also solve this by taking advantage of the second derivative test. In the previous section, if you saw that video, you learned that if you take the second derivative will tell us whether the function is concave up or concave down. And if we combine our understanding of concavity with the value of the first derivative, we can establish whether something is a local minimum or a local maximum. Okay, so let's take the second derivative and we'll see how we use that. Let me go. So now the second derivative of w is going to be equal to the first derivative, the derivative of the first derivative, which was 450 over here somewhere. So before I simplify it, we get to this. So I'll just use this. This is easier to take derivatives from. So minus 450 minus 450 w to the minus 2 power plus 2. That was the first derivative. That's the answer to this first derivative over here. Before simplifying it, right? Afterwards, we simplified it and we got to this level here. Okay, so now we take that first derivative and we take a derivative of that. So we get that p double prime of w equals to positive 900 w to the minus 3 power, and the derivative of 2 is just going to be equal to 0. So the second derivative is equal to 900 divided by w to the power of 3. And now if we evaluate this second derivative at w equals to 15, p double prime of 15 is going to be equal to 900 divided by 15 cubed. And before you calculate that, it doesn't even really matter what the answer is. All we're looking for is whether it's positive or negative, so we know it's positive. Positive. Okay, so we have that w equals to 15 is a critical value. W equals to 15 is a critical value. We know that p prime of 15, the first derivative, equals to 0. And we know that the second derivative at 15 is equal to some positive number. The second derivative equaling positive means that at that point, the underlying function is concave up. This means P of W is concave up. Concave up, right? This gives us information about the graph of the original function P of W. So this tells us that it has a happy face. It's concave up. And we know that the first derivative is equal to 0 when W equals to 15. That lets us know that there's going to be a horizontal tangent like that. And so these two pieces of information combine to let me conclude that W equals to 15 is a local minimum. So W equals to 15 is a local minimum, and therefore it's going to be the value that minimizes the perimeter, right? That's what we're after. Okay, so you don't have to do them both ways. Let me step back here and look at both of them. So we're almost done with this problem, and I did it in more than one way, so it's not quite as long as it was a little longer than it needed to be. So remember that we're interested in finding the dimensions of a rectangle such that the area definitely equals to 225, but at the same time, we want to minimize the amount of length and width, the perimeter, minimize the perimeter. Okay, so here I was just identifying how there's different answers. And so now here's our actual answer. So in general, we have some rectangle, length L, width W. So the area is equal to length times width. Here's the area. The perimeter is going to be equal to 2L plus 2W, right? So we can reduce the number of variables. Focus on the thing you want to maximize or minimize. So in this case, it was perimeter, so we want to focus on this equation. Right? This equation right here is the one that we want to maximize or minimize, because the word problem said maximize and minimize the perimeter. If it had said maximize the area or minimize the area, then we would be working with this equation. Okay, so we want to work with this equation, but there's too many variables. There's the P, there's the L, there's the W. So we use the other equation to help us reduce the number of variables, and we can get to this point. So now we have an equation we can work with. An equation for the perimeter as a function of W. You could have also used L. They'll both give you the same answer. Okay, so now we take the first derivative, we find the first derivative, we can find the partition points, and once we found the partition points, we established that which ones of those fall within the domain of our real-world situation. So in this case, W equals to 15 is the only one that could potentially be an answer. Right now we have to confirm that it's definitely an answer. Now, there was a hint that said, minimize it, so we're hoping that this is a local minimum to our function. So we're hoping it has this sort of a shape. To confirm that right here we really do have that sort of a shape and it's a local minimum, one way to do it is to find a sign chart, define a sign chart for the first derivative. And we want to establish that the first derivative, goes from negatives to 0 to positives, that it is increasing, right? The first derivatives are going from big negatives all the way through to big positives, so you're on your way up. So the first derivative is increasing, means it's concave up, which means that it would establish that W equals to 15 is a local minimum. Okay, so the other way to do it is to think about the second derivative. So if we go back to this function, before we simplified it, maybe it was this one, and take the derivative of that. So that's what I did over here. Take the derivative of that. We found the second derivative. Evaluate that second derivative at the point of interest, the critical value of w equals to 15. We established that it gives you some positive answer. Okay, so when the second derivative is positive, it indicates that the underlying function is concave up. It means that the first derivative is increasing. And so we have a shape that kind of looks like this. And so coupled with the knowledge that the first derivative equals to 0 at w equals to 15, lets me conclude that w equals to 15 is a local minimum. Okay, so that is our answer for w. Now all we have to do is find L, and we'll be done with this problem. So going back to our area formula, we know that 225 must be equal to length times width. And we already know that the width is 15. So we have this formula, 225. So we know that L must also be equal to 15. So there's our dimensions for a rectangle. Both the length and the width must be equal to 15. That'll minimize the perimeter, and the perimeter will be equal to twice 15 plus another twice 15. Remember, there's two L's, two W's, so it'll be equal to 60. 60 is the smallest perimeter you can have and still have an area of 225. Okay, let's see what your author did for this same question. Okay, so if L and W represent the length and width of a rectangle, respectively, we have that the area equals to length times W equals to 225, and that the perimeter is equal to 2L plus 2W. Okay, there's too many variables here, so we got to use this equation to plug it into here. If we let L equal to 225 divided by W, we can plug it back into our perimeter formula, and so that gives us this, right? So that's the same answer we got. And now if we find that first derivative, we get to this, which can be simplified to that. That's what we did. And then we can find the partition points by setting them equal to 0. Good. Or figuring out when it's undefined. So it's undefined at w equals to 0. That's one of the partition points there. And from solving this the way we did above, we get these 2 points. The only one of interest is w equals to 15. So now we've got to take the second derivative of our function. And if we evaluate it at 15, we notice that it's positive, right? So this lets me conclude that it's concave up, which means that w equals to 15 is a local minimum. And so the least perimeter occurs when w equals to 15. And we can solve for L and get that L must also be 15. 15 times 15 equals to 225. And so that's the answer to our problem. A square, it turns out, of sides 15 meters is the rectangle having the least perimeter, where that perimeter is going to be 60 meters with an area of 225. So example 2, maximizing area. A homeowner has $320 to spend on building a fence around a rectangular garden. As shown in the drawing, 3 sides of the fence will be constructed with wire fencing at a cost of $2 per linear foot. The 4th side will be constructed with wood fencing at a cost of $6 per linear foot. Find the dimensions and the area of the largest garden that can be enclosed with $320 of fencing. Okay, so first of all, when you do these problems, make sure you begin by focusing on what it is you want to maximize or minimize. So read the word problem carefully and figure out what that is. So here we're told that we want to maximize the area. The area has to be the largest area possible. And we're talking about a rectangle. So using this over here, this image, I can tell that the area is going to be equal to x times y. So area equals to x times y, right? That's what we want to maximize. And then using the letter A to represent area, we can reduce this down to A equals to x times y. But we still have 3 variables. So we want to bring this down to just 2. We got to come up with another equation that involves x and y, such that I can use that equation, plug it back into here, and reduce this function down to just the a as a function of one of these 2 variables. So that's where all this other information comes in handy. We're told that the cost of creating this thing is going to be $2 for the wire fencing and $6 for the wood fencing. There's only one wall that's going to be wood fencing, and it's of length x, right? It's this one over here. This one over here is also x back there, and this one is $6 per foot. So if we think about the entire price of the entire fence, we are told that it's got to be equal to $320. And from that will be x times 6. However long x is, we got to multiply that by 6. Like if x is 10 feet, we got to multiply it by 6, so it'll be $60. And we also have to include the wire fencing now. So now there's going to be also one more side that is x long, and that would be this one. But this one is only $2 because that one is going to be wire fencing. And there's going to be 2 more sides that are length y plus 2y. That takes care of this one. And then one more over here, which will be another plus 2y. Good. So let's highlight things. So this 6 times x represents the cost to build that wall over there. This 2x represents the cost to build this wall over here. Remember, this one's made out of wire, so it's only $2 per foot. And then we have this one over here, that's this 2y. And finally, we have this one over here, which is that one. Okay, so that represents our entire cost, and then we can simplify that a little bit by saying that this is 320 must be equal to 8x plus 4y, and everything is divisible by 4, so 320 divided by 4 is equal to 80, so 80 equals to 2x plus y. And we want to solve for one of these letters, so why not solve for y, the easiest one? So it would be 80 minus 2x equals y. And now that's what we want to come over here and replace the y over here. So now, bringing this over here, we get that a must be equal to x times y, where y is now replaced by 80 minus 2x. Simplifying it, we get a equals to 80x minus 2x squared. Or a function of x, we can rewrite this as a of x equals to 80x minus 2x squared. Good. And so now we have function notation. From our knowledge of quadratics, we know that this is a parabola that opens down. So it will have a maximum, and that's good because we wanted to maximize the area, find the largest area. So it makes sense that it works that way. Okay, so now let's think about the first derivative. Let's find the first derivative of this function. Put it over here. We found our equation that we want to work with. Function of area. Area as a function of the value x. And so now the first derivative, f a prime of x, is going to be equal to 80 minus 4x to the power of 1. And so now if we find the partition points, a prime of x equals to 0. So we put 80 minus 4x equals to 0. 80 equals to 4x. So 80 divided by 4 equals to x, or x equals to 20 is one solution. And now we need to find y. And we have an equation for y right over here. So y equals to 80 minus 2x. So y equals to 80 minus 2 times 20, which gives you 40, so y equals to 40. So we have our x and our y, but we're not done yet because we haven't confirmed that this is in fact the answer. So you kind of found the answer, but we haven't established that that's the answer. We have to know for sure. So we're suspecting that this is a local maximum. I want to maximize the area. This is going to be the maximum value. So if we think about this graph, well, we know it's a quadratic, so it's going to be a parabola, and we know it opens upside down. So it does have some sort of shape that looks like this, some sort of a concave down situation. And we're hoping we can establish that x equals to 20 is going to be a local max. One way to do that is to confirm that it's in fact the vertex of this quadratic. If you want to do it that way, I'm perfectly okay. Once you get to a point that we know it's a quadratic and that it opens down because the leading coefficient here is a negative, if you want to establish that the vertex is at x equals to 20, that would be fine. But an easier way, or using the methods from this chapter, would be to go over to the second derivative. So now if we take the second derivative of this function, come over here and we'll go f double prime of x is going to be equal to, focusing on this, well, it's just going to be equal to -4, right? Or always negative. Always negative, right? Just taking the derivative of this guy. The derivative of 80 was 0, and the derivative of this is -4. It's always negative. That means that the original function a of x is concave down for all x values, for all real numbers. And we've already established that x equals to 20 is a value such that the first derivative equals to 0. So x equals to 20 is a critical number. F prime, not F prime, A prime. A prime of 20 equals 0, and A double prime of 20 is negative. So all that coupled together allows me to conclude that x equal to 20 is a local max, is a local maximum. And because it's a local maximum, then we've established that it is the value that maximizes area. Good. So we have our answer. This confirms that this is true. Okay, here's a neater solution for this same problem. So we know that we want to maximize the area. So we have we can establish that the area must be equal to x times y. Then we need an equation to reduce the number of variables. So we look at that cost function for fencing. So it's going to be twice the y plus twice an x plus twice another y, and then plus 6 times x. That reduces to c equals to 8x plus 4y, same thing we got before. So we end up with the equation 320 equals to 8x plus 4y. We can solve for either variable, but it makes a little more sense to solve for y. So we have y equals to 80 minus 2x. And then we can use that and substitute it into this equation. And so we get that the area must be equal to x times the new y, which is 80 minus 2x. Distributing it, we get to this equation. So area is equal to 80x minus 2x squared. So now we have area as a function of the variable x. We know that x and y represent dimensions of a rectangle, so both of them must be non-negative. So both x has to be greater than or equal to 0 and y must be greater than or equal to 0. Furthermore, because we know that y must be equal to 80 minus 2x, we can solve for this inequality, 80 minus 2x. Here, let me put that over here. 80 minus 2x is greater than or equal to 0. So 80 has to be greater than or equal to 2x. Dividing both sides by 2, we get 40 less than or equal to x. So x has to be less than or equal to 40, but we also know that x has to be greater than or equal to 0. So that lets us conclude that x must be a value that is greater than or equal to 0, strictly greater than or equal to 0, but less than or equal to 40. So it's trapped between 0 and 40 inclusive. And that's the equation that we want to maximize, right? Area needs to be maximized as a function of x. To do that, we find the derivative of this. So a prime of x is going to be equal to 80 minus 4x. Then we got to find the critical numbers. Set it equal to 0 and solve. So that's how we get that x equals to 20 is the only answer. So now we just have to confirm that that's really our answer. Since a of x is continuous on 0 to 4, the absolute maximum, if it exists, must occur at a critical number or at an endpoint. Don't forget about the endpoints. In the work I did prior, I didn't consider the endpoints because I kind of cheated a little bit. I already knew that this equation was a parabola, and so if it was going to have a local maximum, it would be at the vertex. If the vertex is in the domain. Okay, so if this turns out to be the vertex for this guy, then it would be fine. And we know that x equals to 20 is a place where the first derivative equals to 0. Horizontal tangent line will occur at the vertex point. Right, so all those clues lead me to think that it looks like this. Some sort of horizontal where I know that the derivative of this function, a prime evaluated at 20, leads to 0. So it's going to be horizontal at that point. Okay, but if it wasn't a parabola, just some other random equation, then we know we got to check the places where we have a critical point, but also check the endpoints, right, just to cover all our bases. Okay, so now we evaluate the area at the endpoints, the critical number, and we obtain that the area at 0 equals 0, the area at 20 equals 800, the area at 40 equals to 0. And if you're wondering where those values come from, create a table. So we have a table of values of x, or x could be 0, it could be 20, or it could be 40. So this is our critical number, and these are two endpoints of our variable x, the two endpoints of the subset of our domain that we're interested in. And now we evaluate the original function of x, which is a of x, which is this one right here. So 80x minus 2x squared. So 80x minus 2x squared. So we have 80 times 0 minus 2 times 0 squared. Or we have 80 times 20 minus 2 times 20 squared. Or finally, 80 times 40 minus 2 times 40 squared. And that's where these numbers come from. So that one's an easy one. It's 0. We can use our calculator to confirm that this one is going to be equal to 800. And this one is going to be equal to 0 as well. Okay, so we can see that this is clearly the largest value. It's the only value that's not 0. So there's our answer. Okay, so the largest of these values corresponds to an area of 800 square feet when x equals to 20. With x equals to 20, a equals to 800. It follows that y equals to 40, again using our formula or equation for y. Right there, y equals to 80 minus 2x. using that y equals to 80 minus 2x, and we have that x equals to 20, that leads to y equals to 40. Okay, so the garden should be 20 feet by 40 feet with one 20-foot side of wooden fencing. Okay, so that leads us to a little procedure, a little strategy for solving these questions. So um, read the question very carefully. That's number one. Try and identify all the relevant variables. Maybe take a minute to label them, identify them, define them. We want to introduce variables if we need to. Look for the relationships that are established between the known variables. So we might be looking at equations for areas or perimeters or cost or revenue, right? Some of those known formulas. We want to construct a mathematical model of the form maximize or minimize f of x on the interval I. So we want to focus on what it is we want to maximize or minimize, right? Maximize the area or minimize the cost or maximize the profit. Whatever it is we want to minimize or maximize, that's the equation we want to target on, focus on. So zero in on that equation and see how many variables are involved in that equation. We want to reduce it down to just a one dependent variable that you're interested in maximizing or minimizing, the area or the perimeter or the revenue, whatever it is, as a function of only one other kind of variable. So we might have to use other formulas and use substitution to reduce it down. Once we get it down to a function of the form f of x that we want to maximize or minimize, then we want to find the critical numbers of f of x. And then once we find those critical numbers, we want to use the ideas from the previous section. So we want to find the critical numbers. We want to find those numbers by taking the first derivative, setting equal to 0, taking the first derivatives, figuring out when it's undefined, identify which of those values are in the domain of our function, make sense within the confines of this of our word problem. And then we want to figure out whether we have a local max or a local min at one of those values, or to find the absolute maximum or absolute minimum of f of x on I, which means it could be at the endpoints, right? So we have to consider the endpoints as well. Okay, once we have all of that, come back to your word problem, make sure it makes sense, and answer whatever questions are asked in the problem. All right, let's try another example. Okay, suppose that the homeowners in example 2 decide that 800 square feet for their garden is too small and decide to increase the area to 1,250 square feet. What is the minimum cost of building a fence that will enclose a garden with an area of 1,250 square feet? What are the dimensions of the garden? Assume that the cost of fencing remains unchanged. Recall that one side of the garden was to have wooden fencing and that the other three sides were wire fencing. So if we include a rectangle, remember that we had y and we had x, and x, and that it's $2 per foot for the wire fencing, and then it's $6 per foot for the wood fencing. So the cost is equal to 6 times w plus 2x plus another 2x plus another 2y. Right? So sorry, this thing is messed up here. This is a y here. So if, say, this side over here is wood, the only side that's wood, so we need one of them to be made from wood. Okay, so this is the same as the previous example. And so we had $320 to spend. So 320 is equal to 6w plus, wait, what did I put here? Oh, 8w, erase, equals to 8y plus 4x. And so that's our formula for cost. But now we want to say that we want to increase the area. So this was from the previous example. But now we're saying, well, let's let the cost be a variable. We're not going to fix it to 320. So this is from example number 2. But now we're saying, let's say cost be a movable target as well. We're flexible on that, but we want to minimize it. So this is what we want to minimize. But there's 2 variables. And now the other constraint now is that the area, which is equal to x times y, that area has to be equal to 1250. 1250 equals xy. Okay, so now I can solve for one of those variables, plug it in over here, and then that will help me reduce this equation from 2 variables down to just 2 independent variables down to just 1. So if we solve for either one of these, it doesn't matter which one. Let's pick solving for y. So that means that y is equal to 1250 divided by x. And if we take that and plug it in over here, we get that c must be equal to 8 times the new y, which is 1250 divided by x plus 4x. So we have our new equation. C equals 2. Now if we multiply those two, we get 1250 times 8. 1250 times 8 gets me to 10,000. So 10,000 divided by x plus 4x becomes my new equation that I want to minimize, right? Minimize the cost associated with this equation. So we know we want to take a first derivative, c prime. Now this is a function. Let me write it as a function. So c of x is equal to, and I'm going to rewrite it this way, 10,000 x to the minus 1 power plus 4x, so that I can easily take a derivative. C prime of x is equal to negative 10,000 x to the minus 2 plus 4. And just in case I need it, might as well jump right ahead and do the second derivative. The second derivative is going to be equal to positive 20,000 x to the minus 3 power. Okay, so simplifying it here, I'll get that this means that the first derivative is equal to negative 10,000 divided by x squared plus 4. And from over here, we get that the second derivative of x is going to be equal to 20,000 divided by x cubed. Okay, so we have our the original function that we want to minimize. Then we have our first derivative, and we have our second derivative. Okay, so next, let's think about the critical values around the first derivative. So c prime of x equals to, well, let's combine these two to simplify it. So that'll be multiplying the numerator and denominator of this function by x squared over x squared. I'll get minus 10,000 plus 4x squared all over x squared. And then just twisting it around a little bit and factoring out a 4, we get that c prime is equal to 4 factored x squared minus 2,500 all over x squared. So c prime of x equals does not exist when the denominator equals to 0. So we know x equals to 0 is a partition point. And also we know that f prime of x equals to 0 when the numerator equals to 0. So we set that equal to 2,500 equals 0. So x squared equals to 2,500. And we can take the square root. So x equals to plus or minus the square root of 2,500. Which equals to 50. So x equals to plus or minus 50. Okay, so these are our partition points. Partition points of c prime of x are x equals to 0, x equals to negative 50, and x equals to positive 50. But again, if we think about the value of x, x represents the length of a rectangle in real life, and the length of a rectangle cannot be negative and it cannot be 0. Can't have a rectangle with one of the sides equals to 0. So x equals to 50 is the only possible value, the only critical value. So x cannot be 0, x cannot be less than 0, x must be strictly greater than 0. So x equals to 50 is the only critical value. Okay, now let's think about that second derivative. What's happening around that 50? Well, note that the second derivative, which is right here, 20,000, 1, 2, 3, divided by x cubed, well, the numerator is positive, it's just 20,000. And as long as x is a positive number, when we cube it, we're going to get another positive number. And remember, x is the length of a rectangle. We're never going to let x be a negative. X has to be strictly greater than 0. X must be greater than 0. Okay, so this whole thing is just going to be some positive. We've established that the second derivative is positive for all numbers. So in particular, the second derivative evaluated at 50 is going to be some positive number, right? It's going to be 20,000 divided by 50 cubed, which is going to be some positive number. So that means that the underlying function will be concave up. So c of x is concave up. So in general, it's just going to have this sort of a happy face kind of shape. And now we need to establish, or also establishing, that the first derivative is equal to 0 at 50. So also, since we know that the first derivative evaluated at 50 equals to 0, so these two things, knowing that it's concave up at 50, it's got this sort of a shape, and we also know that the first derivative is equal to 0, those two things help me confirm that x equals to 50 is a local minimum. So x equals to 50 is a local minimum. Okay, so now to figure out the value of y, we use this other little equation. We have that y equals to 1250 divided by x. So let's bring that over here and say that y equals to 1250 divided by x, which will be 1250 divided by 50. Gives you 25. Okay, so we have our answer. We have to be careful of how to translate it back into this word problem. So the x is 50 and the y is 25. So coming back up here, the y is 25, so this one is 25, and this one is 50. So the side that has wire must be 50, and then this side, this length over here, which also has wire, is a value of 25, and then this side, which is wood, would be 25. So we need 25 feet of wooden fencing, and then 50 feet of wire fencing here, and then this translates to 25 feet of wire fencing again, and then finally another 50 feet of wire fencing. Okay, what is the minimum cost of building a fence that will enclose a garden and an area of 1250? Okay, what is the dimensions of the garden? Okay, 25 by 50. Assume that the cost of fencing remains unchanged. Recall that one side of the garden has wooden fencing. Okay, so we've established that that minimum will occur for this function when x equals to 50, but now we have to actually find the value. So if we go back to our cost function, here's our cost function. We can evaluate it at 50. So C of 50 is equal to 10,000 divided by x, 10,000 divided by 50 plus 4 times 50, right? Using this equation or that equation, either way, this one or this one, and evaluating it at 50. So 10,000 divided by 50 plus 50 times 4 is going to be 200. It gets me to 400. So C of 50 is going to be equal to, oops, is equal to 400. Okay, so this is going to be the cost. This is $400. So we're going to have a rectangle where we have wood on this side, and the rest are wire, wire, and wire. The area trapped inside here will be 1250. We know that this length over here is going to be the 50 feet. So this length over here will be 50 feet. And we know that this length over here will be 25 feet. Good. And the total cost to create this garden will be $400. Okay, let's see what your author did here. Okay, same equation. Since x and y represent distances. So in example 2, we found that the cost function was equal to c equals to 8x plus 4y. This represents the cost. This representation for cost does not change if the size of the garden changes. To minimize c equals to 8x plus 4y subject to x times y equals to 1250. Since x and y represent distances, we know that x and y must both be greater than or equal to 0. Okay, so we can use this equation, solve for one of the variables, and plug it into the other. And so we end up with this guy. Good, slightly different from what I did, but same idea. Okay, so then we multiply, take a derivative, figure out when that derivative equals to 0 to find the partition points. We end up with this, which gives you x equals to 25. And then the second derivative is this. Okay, the same thing we got, evaluated at 25. We know it's positive. We know that means that the underlying function is concave up at that point, which means it's a minimum. So the second derivative is positive at only critical number x equals to 25, or x equals to 4x greater than 0. It's a local minimum, absolute minimum. So the cost of the fencing will be $400. X times y equals to 1250, x equals to 25, and y equals to 50. So the minimum cost to enclose 1,250 square feet of garden is $400, and the dimensions are 25 by 50 with one 25-foot side of wooden fencing. Okay, same answer I got. Example 4, maximizing revenue and profit. An office supply company sells X permanent markers each year at a price of P dollars per marker. The price-demand equation is given by P equals to 10 minus 0.001x. What price should the company charge for the markers to maximize revenue What is the maximum revenue? Okay, so focusing first of all on what they want us to maximize or minimize, we know it's revenue. So we need to come up with the equation for revenue and then maximize or minimize that. Figure out the local maximums, figure out the absolute extrema for that function within the constraints of the word problem. Okay, so we know that revenue must be equal to price times x. The price times the number of units, right? Okay, so R equals to price. Well, price is this. That would be 10 minus 0.001x. That's the price, times x units. So if we multiply that, we get that R equals to 10x minus 0.001x squared. And then we can rewrite this into function notation as R of x equals to 10x minus 0.001x squared. Now, both the price and the demand must be greater than 0. So x must be greater than or equal to 0. You can't have negative demand, or in most situations, you really can't have negative demand. And also, the price must be greater than or equal to 0. Again, in most situations, you want your price that you're selling an item to be greater than or equal to 0. Otherwise, you'd be paying people to take your item from you. There are some situations where you do that, but they're not very common. So price is also equal to 10 minus 0.001x. So if we solve for x, we get that 10 must be greater than or equal to 0.001x. Divide both sides, we get 10 divided by 0.001 less than or equal to x. And if we divide those two, we get 10,000. So 10,000 greater than or equal to x. Okay, so combining this with this lets me know that x must be greater than or equal to 0, but less than or equal to 10,000. Okay, so here is our equation for revenue as a function of x, and this is what we want to maximize, figure out the maximum revenue with this as our constraint. So let's find our first derivative. R prime of x is going to be equal to 10 minus 0.002x. And as long as I'm at it, I might as well take the second derivative. Second derivative of x is going to be equal to 0. That's going to be negative 0.002. Okay, so now focusing on that first derivative, let's find the partition points. So we're going to set it equal to 0. F prime of x, set it equal to 0. So 0 equals to 10 minus 0.002x. So that means that 0.002x must be equal to 10. And so x equals to 10 divided by 0.002, which means x is equal to 5,000. Okay, and it's within the domain, so that's our critical number. X equals to 5,000 is our critical number. That might be our answer. We just have to confirm that that's our answer. And we can do that by thinking about the second derivative. The second derivative evaluated at 5,000, well, since it's a constant, note that the second derivative evaluated at 5,000, well, it's just equal to negative 0.002. It's a constant, which is a negative. This lets me know that my original function is concave down, right? The second derivative is negative, means that the original function is concave down. So it's going to look like a sad face. If I look at the graph, it will be some sort of a sad face, some sort of concave down situation. And coupled with this fact that the first derivative evaluated at 5,000 will be equal to 0, lets me know that the tangent line is horizontal there at an input value of 5,000. So all of that combined lets me know that x equals to 5,000 is a local maximum. Okay, so x equal to 5,000 is a critical number. R prime of 5,000 equals 0, and then R double prime of 5,000 is negative. And so all of that together helps me conclude that x equal to 5,000 is a local max, right? And this was a function of revenue. So if we kind of concluded this here, we have some sort of revenue function, r of x, and here's x. And so we've established that when x is 5,000, we'll achieve some sort of local maximum for the revenue. And what is that revenue? Well, to find it, we're just going to have to evaluate our original function of r at 5,000. So r of x, coming back up here, was equal to this equation. 10x minus 0.001 x squared. So it's something, so 10 times something minus 10 times something minus 0.001 times something squared. And we're going to plug in a 5,000 into here, 5,000 into here, and 5,000 into here. And then calculate it. Let's get our calculator. So I'll start with the 5,000, 5,000 to the power of 2 squared times 0.001 gets me that number. And so I'll have 10 times 5,000, 1, 2, 3, minus that previous answer, and I get 25,000. So R of 5,000, R of 5,000 equals to 25,000. Okay, so that's our answer. The revenue will be maximized when x equals to 5,000. Remember, x is demand. When demand equals to 5,000, then the total revenue collected will be 25,000, and that's associated with a price. Remember, the equation for price was this relationship up here. This was the price relationship, so price equals to 10 minus 0.001 times 5,000. And so that equals to 1.21 times 5,000. That's going to be 1. That's going to be 5. 5 minus 5, so 5. P will be 5. Okay, so price will be 5, demand will be 5,000, and total revenue collected will be 25,000. So P is $5, X is 5,000, and maximum revenue, max revenue is equal to 25,000. Okay, here's another solution for the exact same thing. So the revenue equals the price times demand. Revenue equals to the price times the demand. We can distribute that x to get to this. Okay, both the price and the demand must be greater than 0, so that allows us to find a solution for a limitation, a constraint for x. So here's our mathematical model we found. R of x must be equal to 10x minus 0.001x squared, for x being greater than 0, less than 10,000. Same thing I got. Okay, finding that first derivative gets you to this. Set that equal to 0 and solve for x. That's how we get that x equals to 5,000 is a critical number. And then when we found the second derivative, it was always equal to this constant, right? Which meant that it was always negative for any value of x. We know that the underlying function r of x is going to be always concave down, which makes sense here because we can see that this is a upside down parabola. So it's always concave down for any value of x. And so in particular, for x equals to 5,000, it's going to also be concave down there. So combining all three pieces of information, that x is a critical number, that the first derivative evaluated at 5,000 equals to 0, and that the second derivative is negative at 5,000, allows me to conclude that the revenue will have a local maximum at x equals to 5,000, which corresponds to a revenue of 25,000. Okay, so the demand is going to be x equals to 5,000 at a price of $5, and the company will achieve a maximum revenue of 25,000 at a price of $5 per marker. Okay, building on the prior example, example 5. Now, suppose that the company in example 4 has a cost manufacturing markers of C of x equals to 5,000 plus 2x. What is the company's maximum profit? Okay, so from the prior example, we remember that the revenue was equal to 10x minus 0.001x squared. And this was with a constraint for x of x had to be greater than or equal to 0, but less than or equal to 10,000. Good, can confirm that right up here. So the revenue was 10x minus 0.001x squared. And we have that the constraint was right here. Okay, so let me just highlight it right here. Okay, so 10x minus 0.001x squared. So we want to use that to answer this question. Now this question cares about maximizing profit. So if you remember the formula for profit, profit is equal to the total amount collected, the revenue, minus the costs associated. So for us, that means that P of x is going to be equal to R of x minus C of x. So P of x is going to be equal to 10x minus 0.001x squared, that's the revenue, minus the cost, which was 5,000 plus 2x. Simplifying that, we get that the profit function is going to be equal to negative 0.001x squared plus 8x minus 5,000. Right, distributing this minus, we get a minus 5,000, minus 2x, and then we have 10x minus 2x gives us positive 8x. And we still have the same constraint for x. 0 is less than or equal to x, less than or equal to 10,000. Okay, so this is the formula we want to maximize. We want to find the maximum profit. So let's find derivatives. The first derivative of x is going to be equal to negative 0.002x plus 8. And the next derivative, the second derivative of x, is going to be equal to just negative 0.002. From the first derivative, we can find the partition points. So we can set that first derivative equal to 0. And we get negative 0.002x plus 8 must be 0, right? And we solve for x, we get that 8 must be equal to positive 0.002x. And so 8 divided by 0.002 must be equal to x. So 8 divided by 0.002 is equal to 4,000. 4,000 equals to x. Okay, so this is a partition point. We set the first derivative equal to 0, so that means that 4,000 is a partition point. And since 4,000 is in the domain, the interested area we're interested in, that means that we can upgrade it and say that x equals to 4,000 is a critical number. Okay, so x equals to 4,000 is a critical number. And we've just established that the first derivative at 4,000 must be 0. And if we think about the second derivative at 4,000, second derivative evaluated at 4,000, well, it equals to a constant, so it's equal to negative 0.002, which is just a negative. Okay, so just put that over here. Second derivative evaluated at 4,000 equals some negative. Okay, the second derivative is negative at that point, means that the function, the underlying function p of x, is going to be concave down. Right? If we have some sort of a graph depicting the profit as a function of x, so this is going to be some p of x, then we know that at x equals to 4,000, there will be a local max. X equals to 4,000 represents a local maximum because we know that the tangent line is going to be horizontal at that point. The tangent line equals to 0, and we know that the function is concave down at that point. So together those two things let me conclude that x equals to 4,000 really is a local maximum. Thus, x equals to 4,000 is a local max. So demand must be 4,000. What about price? Price, we said, was equal to, let's go back up and find our price equation. Price was 10 minus 0.001x. Price is equal to 10 minus 0.001x. And we just established that x in this scenario, this situation, is equal to 4,000. So we need to figure out what this is. 001 times 4,000, 10 is that, equals to the price. Oh, this p and the price and the profit look a little confusing, huh? So let me spell it out. The price is equal to this. So we can calculate it. Times 0.001 is 4. 4 minus 10, so the price is going to be equal to 10 minus 4, or price will be 6. And what about the actual profit then? What's the profit going to be? Well, we know it's going to be maximized when x equals to 4,000. There's an extra 0 there. So let's evaluate our profit equation at 4,000. So coming back up here to our equation for profits, that's this one. We evaluate this equation at x equals to 4,000. So p of blank equals to negative 0.001 blank squared plus 8 times blank minus 5,000. And we want to evaluate this at x equals to 4,000. Okay, so let's get our calculator. So 4,000 into 3, the power of 2, times negative 0.001 plus, and then 8 times 4,000 gives you that, minus 5,000 gives you that. So I get a profit of 11,000. P of 4,000 equals to 11,000. Okay, so putting it all together, demand is 4,000. X equals to 4,000 is demand. We see that the price is equal to $6. Price was $6. And now we get that the profit is 11,000. Okay, so when we set a price of $6, we expect to sell 4,000 units, and we will maximize our profit, and that profit will be 11,000. Okay, given the conditions we're considering, that's the most amount of money you can make, 11,000, by setting it equal to $6. If you set it to $7, you would think, oh, more money, it's more expensive, you'd make more, but that's not true because demand goes down. The more expensive an item is, the less that people are going to want it. And so if you make it a little more expensive, then demand will go down a little bit, and so you'll end up making a little bit less money. Likewise, if you lower it a little bit from the $6, you make it $5, you lower the price, you're going to increase demand, so you're going to sell more units, but at a smaller price, and then you'll end up cutting into your profit, so you'll make less money. So the sweet spot is to let X equal to 4,000 or the price equal to $6, which will result in a maximum profit of 11,000. Okay, so here's what your author wrote down. Exact same thing, but just really compact, so it might be hard to follow. So profit equals to revenue minus cost, right? So here's our revenue equation. Here's our cost equation. We can combine those, simplify them to get this. This is the same equation we got. So here is the model we want to maximize. P of X, profit, remember in this case capital P is profit, equals to 8x minus 0.001x squared minus 5,000. And we have the same constraint for x. It must be greater than 0, less than 10,000. Okay, so we take a first derivative, we get to this. Set it equal to 0, solve for x, we get to the 4,000. Okay, it is a value within our constraint for x, so it is a critical number. Now we take the next derivative, it equals to a constant, so it doesn't matter what x is, the second derivative will always be negative, which means that the underlying function p of x is always concave down. Good. So x equals to 4,000 gives a maximum profit. We can see that because x equals to 4,000. The first derivative evaluated at 4,000 equals to 0, and the second derivative is negative at x equals to 4,000. That combined, those pieces of information combined let me know that x equals to 4,000 must be a local maximum. And so the maximum profit is going to be realized for 11,000. So we plug this into our original function p of x to get the 11,000. And then we can use the formula for price, the price demand equation to find the value for the price, which is the same we got before, $6. And so the maximum profit of 11,000 is realized when 4,000 markers are manufactured and sold for $6 each. All right, example 7, maximizing revenue. A management training company finds that a price of $80 per person, at a price of $80 per person, 300 people will attend their seminar. For each $8 decreasing price, an additional 50 people will attend. How much should they charge in order to maximize revenue, and what is the maximum revenue? Okay, so we have a particularly established relationship between price and demand. So when the price equals $80, we see that that translates into a demand, D, of 300 people. And then we see that there is a relationship established by these multiples of 8. For each $8 decrease in price, an additional 50 people will attend. So we need a variable to represent the multiples of 8. So it doesn't matter what letter you use. How about A? Let A equal the number of $8 decreases in price. So for example, we can do like a quick little table just to confirm what this means. So if we have A there and then we have the price there, the price then is going to be equal to 80 minus 8A, right? So when A equals to 1, we do one multiple of the 8, we will get that the price is 80 minus 8 times 1. When A equals to 3, for instance, 3 multiples of A, that would be 80 minus 8 times 3. That'll be 24, which gets you to 66. So the price would be 66. And over here, the price was 72. Okay, and then there is also a demand associated with these. When A equals to 1, the demand says that for each multiple of 8 decrease, there's an additional 50 people, 50 people that will attend. So the demand is going to be equal to 300 plus 50A. So when, for example, when A equals to 1, we get that the demand is going to be equal to 300 plus 50 times 1, or 350. And when A equals to 3, we do 3 price drops. It'll be 300 plus 50 times 3, which means the demand will shoot up to 450. Okay, so as the price drops by multiples of 8, the demand will increase by multiples of 50, right? They're all tied into this variable A. Okay, so we have a formula for the price. So the price is going to be this $80 minus 8A, and we have a formula for the demand. Which is going to be 300 plus 50A. Now the price has to be positive, so price has to be greater than 0. And so we get 80 minus 8A must be greater than 0, which means that 80 is strictly greater than 8A, which means that 80 divided by 8 is strictly greater than A. So 10 strictly greater than A. So A must be less than 10. Okay. Now, can A be a negative number? What would happen if I come back over here and replace A with, say, -1? What am I really doing? Well, then I would be doing 80 minus 8 times -1 minus 1, which means I would be adding, right? The price at that point then would be 88. So yeah, you could let A equal to a negative, except that this problem said for each $8 decrease in price, they're kind of highlighting that you're going to be decreasing the price. So making the decrease in price a negative, meaning that the value actually goes up, seems kind of counterintuitive to what they're looking for. So I think we should just stick to letting A be strictly greater than 0. Right? We want to figure out the multiples of 8 that we want to decrease. So that's the constraint we have for A. Now, the thing they want us to maximize is revenue. So remember that our revenue function, is going to be equal to the multiplication of price times demand. Price times demand. Good. And we have formulas for both. So the price is going to be this 80 minus 8a, and demand is 300 plus 50a. So we can rewrite this as, in function notation, as r of a. R of a equals to this, and so I can FOIL it and get that r of a equals to 80 be 24,000 plus, it's going to be 4,000a, 4,000a minus, that's going to be 2,400a minus 400a squared. Okay, so simplifying that, we get that r of a equals to 24,000 plus 1,600a minus 400a squared. And then flipping that around, we get r of a equals to minus 400a squared plus 1,600a plus 24,000. Okay, and we have a constraint that a is less than 10, but a must be greater than 0. It could be a decimal value, right? We could take a decimal multiple of the 8, like say half. Okay, so now this is what we want to work with. Okay, so this is the function that we want to maximize. So let's start taking derivatives. So r prime of a is going to be equal to negative 800a plus 1,600. That's a 0. Let's go ahead and take the next derivative as well. So then r double prime of a, second derivative, is just going to be equal to negative 800. Okay, so we know that because it equals a negative as a constant, that this function is concave down for all values of a. So certainly it's concave down for a between 0 and 10. And that makes sense because this is a quadratic that opens down. Okay, so now looking at this guy, if we set that equal to 0, and prime of a equal to 0, we get negative 800a plus 1,600 equals 0. So a equals to negative 1,600 divided by negative 800, so a equals to 2 as our critical number. Right? 2 is in our domain, so a equals to 2 is our critical number. A equals to 2 is the only critical number. The only number. And we get that from the fact that our prime of 2 equals 0. And because the second derivative is always equal to negative 800, we know that it equals to negative 800 when we evaluate it at 2, or that it equals a negative number. So all that together lets me know that we have a local maximum at a equals to 2. Thus, r of x has a local max at x equals to 2. And now if we want to find the actual value of our revenue at 2, we have to evaluate our original function at 2. So going back to our function there, we end up with minus 400 blank squared plus 1,600 blank plus 24,000. And we evaluate it at 2, 2, and 2. And we get that r of 2 equals 4 times 400, that's minus 1,600, plus 3,200, plus 24,000. So So that's going to be R of 2 equals to positive 1,600, 25,000, 26,000. Equals 1,600 plus 24,000 equals to 25,000. 2 equals to 25,600. And that's going to be our maximum revenue. So 2 is not the price, right? So A equals, oops, where did I jump to X? Sorry, right here. This is not an X. This is not an X. This is an A in the variable A. So thus, R of A has a local maximum at A equals to 2. Okay, but A equals to 2. A is just the number, the multiples of discounts that you're going to have. It's not the price, so now we still have to come back and find the price and find the demand. So coming back up here, the price was given by this equation, and demand was given by this equation. And we've just established that A equals to 2 is going to be what maximizes the revenue. So price then, going from there, so the price then would be equal to 80 minus 8 times 2. So 80 minus 16 is going to be the price. So that's going to be 64. The price is equal to 64. And the demand will be equal to 300 plus 50 times 2. So the demand will be 400. It makes sense, hopefully, that the revenue, just to confirm we get the same answer as before, the revenue, which is equal to price times demand, should be 64 times 400. And so that revenue achieved at that point would be 64 times 400, which is 25,600. 25,600. Okay, so if you set the price equal to $64, the price equal to $64, the demand will be 400. That's how many people will buy the tickets. And the revenue will be 25,600. Okay, so roughly, just a rough sketch of what's happening. We have some sort of equation like this, where A is this, and then we have some R of A like this. We know that R of A is a parabola that opens down, so it's going to have some sort of a general shape, like that. I'm not really sure where it crosses the horizontal axes or the vertical axes. Doesn't matter. Just in general, it'll have some sort of shape like that. We know it's concave down everywhere. Second derivative is negative. And we've just established that when when the input value is A equals to 2, we reach some sort of a max there, and we have a local maximum there. So when A equals to 2, the price is going to be $64, the demand is going to be 400, and total revenue is going to be 25,600. If you change this just a little bit, like maybe you decide to go at A equals to 3, and A doesn't have to be a whole number, it could be a decimal value as well. So maybe it could be 2.5 or 2.1 or something like that. So if you decide to change the price from something other than 64, maybe you decide to go down to 63 or you decide to go up to 65, then you're not going to achieve your maximum revenue. If you increase the price just a little bit, maybe $65 or $64.50, right? Even just a little bit of an increase in price from this point will result in a demand that's a little bit lower, and then the product of the two will result in a smaller revenue. Likewise, if you decide to lower this by just a little bit, $63, $63.80, any amount, just a little bit less than this, then you will increase demand, lower price, increase demand, but the product of the two will still be lower than this, right? So this is the maximum revenue that can be achieved, and it will be achieved when A equals to 2, price equals to $64, and demand per unit or per ticket, and demand will be about 400. Okay, so that should be more than enough to tackle your homework. As usual, please come to my office hours if you have any questions.